Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Welcome back to a video on implicit differentiation. This is the second video in the series on implicit differentiation. The previous video should have introduced you to implicit differentiation. You should be somewhat familiar with the mechanics of it. You should know that all implicit differentiation is using the chain rule without immediately solving for y first. That's basically what it comes down to. In this video, we're going to cover kind of the oddball questions that usually get asked when working with implicit differentiation. I tend to find that implicit differentiation is much more preferable to regular differentiation in most situations because it takes me time to solve for y. And if I don't want to solve for y, what's the point? Just go ahead and implicitly differentiate. So let's see how that works here. Use implicit differentiation to find the equation of a tangent line to the curve at the given point. One thing that students hate about implicit differentiation is the fact that they have to solve for dy dx. It's the algebra at the end, that's what they hate. But when asked to find the equation of the tangent line at a point, you do not actually have to go through and solve for dy dx. Let's see why. First of all, what do you need for the equation of a line? You need a slope and you need a point. Luckily, they've given us a point, so we just need the slope at that point. And I'll denote that slope at that point as dy dx at the point 1, 0. We want the slope at that point. Once we have that, we have the equation of the line, basically, of the tangent line, that is. So let's go ahead and find out what dy dx is. Taking the derivative of both sides with respect to x. And this time, since we've already gone through the mechanical video, I'll speed up only slightly, but I'll still speed up a little bit. The derivative of x squared is, well, 2x. The derivative of sine is the cosine of whatever its argument is. But then by the chain rule, you have to hop inside this sine function and take the derivative of its interior. The derivative of its interior, well, that's a product rule. Derivative of x is 1 times y plus x times the derivative of y with respect to x. Plus, the derivative of something cubed is 3 times that something squared times the derivative of the something itself. And that's equal to the derivative of 1, which is 0. Now again, as I mentioned a few moments ago, probably the thing that students hate the most about this style of problem is that they have to solve for dy dx. But again, when I'm finding the equation of a tangent line, nobody's actually asking me to solve for dy dx. They're just saying, hey, find the derivative at this point. Once you have found once you've taken the derivative, substitute in the point that they handed you. Be warned though, only substitute in that point after you have taken the derivative, not before. If you substitute in that point, 1, 0, before you take the derivative, you'll get a bunch of constants. And derivatives of constants are 0. You're just gonna zero everything out. So instead, take the derivative, like we have, and then say, well, I'd like to find dy dx at 1, 0. So we're gonna let x equal 1 and y equal 0 in our derivative equation. If you do that, that will imply that you have 2 times 1 minus the cosine of 0 times 0 plus 1 times y prime plus 0 is equal to 0. Notice how nice and clean that is when I substitute those values into x and y for our derivative equation. Very, very clean. We know the cosine of 0 is 1. So this is just going to be 2 minus y prime is equal to 0. Or in other words, y prime is equal to 2. Very nice. By the way, I should say at 1 comma 0. So y prime, the derivative, is 2 at 1 comma 0. So now we know what dy dx at 1 comma 0 is. It's just 2. We have the point, and so the equation is going to be y is equal to 2 times the quantity x minus 1. It's y minus 0 is equal to 2 times x minus 1, but you get it. So that implies our equation of our tangent line to the curve at that point is 2x minus 2. And just to showcase that, here's the curve. Kind of a nice looking curve, right? Interesting, at least. And let me turn on our tangent line that we just computed at the point 1 comma 0. And that is, or at least very much looks like, it's the tangent line at 1 comma 0. So we just finished an example of finding the equation of a tangent line to an implicitly defined curve. And we learned that implicit differentiation is not as bad as it originally seemed when you're asked to find the equation of a tangent line. You just find the derivative, but you don't need to actually find or solve for explicitly dy dx. You just need to first take the derivative and then substitute in the point. However, in normal situations, you do actually have to solve for dy dx if you're not asked to find the equation of the tangent line. So if they just say, what's dy dx, then you have a little bit of algebra in front of you. In this example, we're going to go ahead and use implicit differentiation in a different format. This is kind of one of those questions you see where it involves the idea of implicit differentiation without stating it. So if you have a function that when you raise to the fourth power is equal to the third power of the function plus x, and if you know that the function evaluated at 1 is 2, find f prime at 1. Now that seems a very robustly weird problem, but the real goal is to find f prime and evaluate it at 1. So let's go ahead and see if we can find f prime given this information. F prime is just the derivative of both sides. So the derivative of this left-hand side, well, it's a function raised to the fourth power. The derivative of a function raised to the fourth power is 4 times that function raised to the third power. But then you have to hop inside of that power there and take the derivative of its argument. The derivative of f itself is, well, the derivative of f. It's f prime. On the right-hand side, you have a function, not the same exact function, just a different looking function, raised to the third. The derivative of a function raised to the third is 3 times that function raised to the second. The function itself, x plus f of x. And what we need to do is, once we've taken that outer derivative, take the derivative of the argument, the interior. We'll attach that via parentheses. Right there, the derivative of x is 1. The derivative of f is f prime. We've gotten this far, and we're asked not to find f prime of x. If they asked us to find f prime of x, I would then solve this for f prime of x. But in reality, they're only asking us to find the value of f prime at 1. So at this point, I'm just going to let x equal 1. Doing so at this point, rather than solving for f prime explicitly, saves me a lot of work. Just start by allowing x to equal 1. You can do this because you've already taken the derivative. Remember what I said in the previous example. Take derivatives first, then plug in points, not the opposite. So we've taken the derivative, let's plug in the point. Letting x equal 1, we have 4 times f at 1 to the third power times f prime at 1 should equal 3 times 1 plus f at 1 being squared times the quantity 1 plus f prime at 1. Well, luckily they told us what f at 1 is. It's right here. So all of those f of 1s will be traded out for 2s. So let's go ahead and trade out all the f of 1s for 2s. It'll be 4 times 2 cubed times f prime at 1 is equal to 3 times 1 plus 2, or 3 squared, times 1 plus f prime at 1. Cleaning things up, let's see, it's 8 times 4, or 32. F prime at 1 must equal, let's see, that's 27 times 1 plus f prime at 1. Now you can see what's going to happen, right? You distribute that 27 through, and it just becomes an algebra problem at this point. 27 plus 27 f prime at 1. Subtract 27 f prime of 1 from both sides, and you'll get 5 f prime at 1 on the left-hand side is equal to 27, or in other words, f prime at 1 is equal to 27/5. So each step of the way, nice clean work. Remember, started with taking the derivative. After taking the derivative, we let x equal 1. And then from that point forward, it was just an algebra problem, slowly solving for f prime at 1. Now we arrive at a point where we need to make a strong distinction using Leibniz notation, because we haven't been able to do this in the past. So here is an equation. It's implicitly defined equation. So we could, I suppose, solve for one of those variables, s. We could solve for s if we wanted to. But if you note, all of our derivatives are the derivative of r, derivative of r. We do have a derivative of s right here, and then a derivative of t. So solving for an explicit variable is not going to help out when we're asked to take derivatives with respect to other variables all the time. So now we get to actually play with Leibniz notation the way it's meant to be played with. We're going to take the derivative of both sides of this equation with respect to t first. We'll find the derivative of r with respect to t, considering that s is a constant. So s is going to just be some constant for us, like a 5 or a -2 or something like that. So let's go ahead and do that. It plays just like all the other implicit differentiation problems we've done, with the exception that we do have some variable in there that is no longer a variable. That's totally okay. So let's do this. The derivative of the left-hand side. So d dt, I'll write this out. There we go. Now remember, s is a constant. So let's see, this implies derivative of r squared. Well, that's twice r to the first times the derivative of that r with respect to t, because that's what we're taking the derivative with respect to, plus the derivative of 2s, which is a constant, times t to the 1/2. Well, that's 2s times the derivative of t to the 1/2 with respect to t. Well, s is bothering me. The derivative of t to the 1/2 is 1/2 t to the -1/2. And if you really wanted to, you could say times the derivative of that t, but you're taking that derivative with respect to t. So that's going to be a 1, but you could totally do that if you want to. On the right-hand side, we have a product of two functions. So it's going to be the derivative of the first with respect to t times the second, plus the first times the derivative of the second with respect to t. Again, dt dt is just 1. So having done that, we get this. 2r dr dt plus, let's see, the 1/2 and the 2 cancel. So s t to the -1/2. dt dt is 1 minus t dr dt plus r. Solving for dr dt, it's just an algebra problem at this point, so I'm just going to quickly do it. We get the following. Now, that is going to be different than the derivative of r with respect to s. So let's go ahead And now switch to part B. Let's go ahead and redo that problem. I'll do it in a different ink. The derivative with respect to s, considering that t is now going to be a constant. S is a variable, R is a variable, but t is a constant. This is kind of an interesting problem. So let's go ahead and do this. Derivative, part B, derivative with respect to s of both sides, r squared plus 2 s t to the 1/2. Notice I always replace those square roots. D ds of rt. Okay, let's do this. And t is a constant. So wherever you see a t, it's just a number. Well, this would be, let's see, the derivative of r squared, a variable squared, is twice that variable, then derivative of that variable with respect to s, plus t is a constant and 2 is a constant in this problem. So this is 2t to the 1/2 times the derivative of this s, but with respect to s. We know that's going to be 1. Equals. Now you might think this is a product of functions, but it's not. T is constant. Let me write that again. T is a constant, so we can go ahead and say, well, that's just t, whatever that number is, times the derivative of r with respect to s. Now remember, our goal was to find dr ds, so we'll go ahead and isolate. Remember, ds ds is just 1. I'll go ahead and maybe I'll move everything. No, I prefer, well, I'll move everything over the right-hand side. So 2t to the 1/2 is equal to dr ds times t minus 2r. And then I'll divide both sides by t minus 2r. So this is what we get. If you need to slow down on the algebra, then pause and do it by hand, and you'll see that's correct. So there we go. That is the derivative of r with respect to s, given that t is constant. And then you can go through and do each of these. I think that those two are fine. Let me see if there's anything special about the other two. Yeah, I think the D is actually kind of interesting. So I'll go ahead and finish off with D, and I'll again just let you know that C you could totally do on your own. We're going to hold R as a constant here, which means that when I take this derivative of both sides of this equation, this guy right here is a constant, and derivatives of a constant will be 0. That's what I think is kind of interesting about this one. So let me write down the derivative. We are taking the derivative with respect to s, in this case, of both sides. So of r squared plus 2st to the 1/2 and equals the derivative with respect to s of rt. Remember, r is a constant. So let's go ahead and do this. Derivative of r squared, well, r is a constant, so the derivative of a constant is 0. Plus 2 times the derivative with respect to s of st to the 1/2. Those are two completely different functions, completely different variables. So that will be a product rule. On the right-hand side, however, r is a constant. And so that is not a product rule. That is just r times dt ds. Now we just need to go through and take this product rule. Derivative with respect to s of s is 1 times t to the 1/2 plus s times the derivative of t to the 1/2, which is going to be 1/2 t to the negative 1/2, and then times the derivative of that t with respect to s is equal to r dt ds. And remember, we're trying to find out what dt ds is. So it becomes an algebra problem solving in this case. So it's 2t to the 1/2 plus st to the negative 1/2 dt ds is equal to r dt ds. And not to bore you, I'll just quickly solve this out. When we get there, technically I can multiply numerator and denominator by t to the 1/2 power, and I would get the following: 2t over RT to the 1/2 minus S is equal to dt ds. But that's neither here nor there. A little bit of algebra in there. But that's kind of the distinction. That's why we use Leibniz notation. So we could say, here's a function involving a bunch of variables. Take the derivative of this one variable with respect to this other variable. There are a lot of combinations you could do in this problem. I only selected 4 of them, and we only did actually 3. And now we really get into some synthesis style questions. Show using implicit differentiation that any tangent line at a point P to a circle with center O is perpendicular to the radius OP. To do this, you have to recall that the equation of a circle centered at some point, which we will go ahead and call h comma k, with radius r, let's go ahead and just draw in a radius here. And I will just point it this way. It doesn't actually matter, but this length is r. The equation of that circle, we should already know, is the quantity x minus h being squared plus the quantity y minus k being squared is equal to r squared. That's the equation of the circle. This point on this circle, you can label it however you want. I'm going to call it x1 comma y1. And our goal, that's a terrible parenthesis, let me zoom in and fix that. All right, our goal is to show that the tangent line, which I'll draw in blue right here, is perpendicular to this radius r. The line that, the radius is also considered a line segment, so that line segment r. So let's see, if I know that, or if I want to prove that the tangent line is perpendicular to that radius line segment r there, I need the slope of the radius line segment and I need the slope of the tangent line. The radius line segment is kind of an easy one to find the slope of, so let's go ahead and start there. A little bit of algebra tells us the slope of the radius, which I'll call m sub r, is going to be the difference in the y values, so y1 minus k, divided by the difference in the x values, x1 minus h. So that's the slope of the radius. Now I really hope we can find that the slope of the tangent line is the opposite reciprocal of that. And the way you could do that is to take the derivative of this and evaluate the derivative at the point x1, y1. That is, our goal is to find the derivative at the point x1, y1 and see if it equals the slope of that radius, which is going to be y1 minus the opposite, sorry, not equals the slope, but the opposite reciprocal of the slope. There we go. That's the opposite reciprocal right there. Sorry about that. So we have the slope over to our left-hand side in black, and you can see that would be the opposite reciprocal of it. So that would showcase that the slope of the tangent line is the opposite reciprocal of the slope of that radius, or that those lines are perpendicular basically. So let's go ahead and find out what the derivative of this is. Derivative of something squared is twice that something to the first power times the derivative of its interior. The derivative of that interior is just 1. Plus the derivative of the next term. Well, it's the term is being squared, so the derivative of a square is twice that function times the derivative of the interior. Remember, k and h are constants, but y is not, so this will be times the derivative of y with respect to x. The right-hand side is a constant as well, and so the derivative of that will be 0. And now what I can do is I don't actually need to solve this for dy dx quite yet. I could go ahead and substitute in the values x1 and y1 for x and y. So let x equal x1 and y equal y1. If you do that, you'll have twice x1 minus h plus twice y1 minus k times dy dx is equal to 0. Move things to the other side. You'll get that dy dx, once we have plugged in the point x1, y1, is equal to a negative. This is just moving this guy to the other side, and it'll become a negative x1 minus h. And you're going to divide both sides by y1 minus k. The 2's will cancel in the division. And is that what we wanted to get? Yeah, actually, it's exactly what we wanted. We wanted to showcase the slope of the tangent line at that random point is the same as the opposite reciprocal of the slope of the radius at that point. And therefore, the radius must be perpendicular to the tangent. So this implies radius and tangent are perpendicular. There you go. I used that perpendicular symbol there, right? Tangent line to a circle is perpendicular to the radius. There we go. Good proof. Our very last example in this video requires us to really kind of sketch out a rough idea of what this situation is asking us about. Where does the normal line to the ellipse at the given point intersect the ellipse a second time? The first thing you should note about the ellipse that they've handed us is it's not a standard ellipse. It's off kilter. That is, its major axis is neither horizontal nor vertical. This is a slanted one, and the only way I know that is just because it has a term involving a product of x and y. So that's just kind of a heads up. It's hard to graph this by hand if you have not learned how to do that. But it looks something like this. I mean, not exactly like that, but something like that, okay? And we have this point on the curve, and let's just pretend you don't actually need to truthfully get a beautiful graph of this, but you just know that they're telling you it's an ellipse. They're telling you have a point on it, -1, 1. At least I think that was the point, yes. And they tell you that the normal line to that, you want to know when the normal line to that strikes the curve a second time. Remember, a normal line is perpendicular to the tangent line at that point. So that's a prerequisite for this problem. You have to know what a normal line is. First, you would find the tangent, and then the normal line has a slope opposite reciprocal to the slope of the tangent at that point. All right, so this is really what we're trying to find. That's our goal. Find that guy right there. Now, there are a lot of things going on, and you have to really kind of organize your thoughts. If I could find out the equation of that red normal line, and since I have the equation of the ellipse, I really just want to know when is the red normal line equal to the black ellipse. So that's our ultimate goal. Solve the equation, line equals ellipse. That's basically what we're going to do. I mean, it's not really an equation. You're going to probably do some type of substitution, but that's the idea. Well, but we don't have an equation for the normal line. How do you find the equation for the normal line? Well, you can get it because you have a point on that normal line. So we'll break this into groups here. So I'll look at the normal line. To find the equation of a normal line, I need a slope. I'll call it slope subnormal, and a point. We have a point, -1, 1, on our normal line. They gave us that, so perfect. But we don't have a slope. So how do you find the slope of the normal line? Well, you need to find the slope of the tangent line at that very same point and take its opposite reciprocal. So that means I have another step in my process here. I'll just go to tangent line, and we'll need the slope of the tangent line at -1, 1, because the slope of the normal line is going to equal the opposite of the reciprocal of tangent slope. I'll just say it that way. So this is kind of the thought process that I go through. So I just think kind of where I need to end. I need to find out when that black curve meets the red line. Great. And that means I need the equation of the red line. I already have the equation of the black curve. To find the equation of the red line, I need a point and a slope. To find the slope, I need the slope of the tangent line. And I can do that. It's like a little bit of a domino game here. So let's go ahead and find the slope of the tangent line first. The derivative of that equation is going to be 2x minus a product rule. Derivative of x is 1 times y plus x times the derivative of y. That's a y prime. I'm just using that notation because it's fast. Plus the derivative of y squared is 2y times y prime is equal to the derivative of 3 is 0. And now I'm going to substitute in -1 for x and 1 for y. Let's go ahead and do that. So this is going to give us, we have -2 minus 1 minus y prime. And this time I'm not going to write y prime. I'm going to write dy dx at -1 comma 1, because that's really what we're evaluating at this point. Plus 2 times 1 times dy dx at, at -1 comma 1, and that's all equal to 0. Well, that's super nice. -2 minus 1 is -3. I would move that to the other side. And collecting like terms and all the fun stuff, you get 3 dy dx at -1 comma 1 is equal to 3, or in other words, dy dx at -1 comma 1 is equal to 1. So we know the slope of the tangent line at that point is 1. So I happen to know slope here of the tangent is equal to 1. Equals 1. And therefore, the slope of the normal line equals a -1 over 1. I should write that in red, because it's the opposite reciprocal. And now I can find the equation of the normal line. So the equation of the normal line is going to be y minus 1 is equal to a -1 times x plus 1. Or in other words, y is equal to a -x. Let's see, -1 plus 1. That's it. All right. And now I want that red line, the red normal line, to intersect the black curve. So I want their x and y values to be the same. So I know that the normal line, every single y value on that normal line is equal to -x. So I just want to take that -x and substitute it into this equation. So here we go. I'll write this in black because now we're back to the ellipse. I'm going to sub in y equals -x. That's supposed to be an equal sign, but it didn't work out for me. Equals -x to the ellipse formula. Or ellipse equation, I should say. So let's do that. The ellipse equation is x squared. What it's going to do is it's going to return to me, once I solve, all the x values where the normal line and the ellipse meet up. So I'll get x squared minus x times a -x plus a -x being squared is equal to 3. So let's see, that's x squared plus x squared plus x squared is equal to 3, or in other words, 3x squared is equal to 3, or in other words, x squared is equal to 1, or in other words, x is equal to plus or minus 1. So it tells me that our line, our normal line here, strikes the ellipse at x equals -1 and x equals +1. Now I just need to find out what the corresponding y value is, and that just means go to either your ellipse, or better yet, go to the equation of the normal line and plug in 1 for x, and you'll get a -1 for y. All right. Now let's see if that holds mechanically or on Desmos. Here is the curve in black. There's the normal line in red, and that is y equals negative x that we found. And you can see, yes, it does intersect the curve at -1, 1 and 1, -1. So our mathematics was good. That's always nice to hear, right? All right, so that ends this video on synthesis questions for implicit differentiation. And you're not done with implicit differentiation. There's actually a video after this, which is super duper important because it's derivatives of inverse trigonometric functions, which is critically important for calculus 2.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much. That isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.